Let's work on one of the example. This example, we are given the information xc, yc, and zc. Try to figure out theta 1, theta 2, theta 3. As we discussed earlier, there is no systematic approach to find out the corresponding parameters. So what we're trying to do is to use geometry method to figure out what theta 1 and theta 2, theta 3 is going to look like in this specific robotic system with 3 rotational joints. Okay, so let's get started. First, we are given xc, yc, and zc. We are trying to find theta 1, theta 2, and theta 3. So let's see what we can do to find out the uh, coefficients. So for the angle theta 1, this is located on xy plane. For theta 2 and theta 3, it's on the three-dimensional plane. So it will be more difficult when we have all three components involved, xc, yc, and zc all involved. So we are not going to deal with theta 2 and theta 3 at this moment. We try to figure out theta 1. So for theta 1 over here, what we're really looking at is to find out this triangle. If you project this one onto xy plane, all we have is you draw a line and project that onto xc and onto yc. This is going to be our theta 1. So if you have this configuration, the angle is pretty straightforward to be figured out. That is going to be tangent theta 1 equals to yc over xc, or theta 1 equals to arctangent yc over xc. When you are doing those kind of calculation, you're going to find out in your textbook it's going to be arctangent to yc and xc. Both of them are going to be fine because one is mathematical representation, the other one is we try to figure out using MATLAB function or other computer program to help us to determine the angle of xc and yc. When we are using this one, the positive and negative direction of xc and yc matters because it might be located at within first quadrant or in the third quadrant. They are having the same sign after calculation. So if we need to know which quadrant the position is located, we need to put positive and negative sign in front of xc and yc. So after we solve that one, then we're going to project the rest of the part onto a two-dimensional displacement. So this time, instead of having everything in three-dimensional drawing, we just cut this point and project that into this one. So we actually have z naught over here, but on the horizontal axis over here, we do not put x, y, or z over here. We know its direction of r, but we never determine which direction it's going to be because it's not part of x, y, or z. So if we do something like this, if you view from this side, you're going to find the first joint over here, and it's going to have a second link over here, link to this one. Then the distance between the center of the second roller rotational joint, and the end effect is going to be R. Let's name, and we know this is going to be S based on the information over here. This is going to be ZC minus D1. Okay? Secondly, we know this one is theta 2. This one is theta 3. The length over here is A2 and A3. So with those information, we're going to figure out what is theta 2 and theta 3. You might have other method that trying to figure out other part of the information, but it doesn't matter what you do. You need to solve for theta 2 and theta 2 in the end of the solving procedure. So let's do that. If you draw everything like this one, let's repeat what we did earlier. We will need to put theta 2 over here and theta 3 over here and A2 and A3 over here, so it's easier for us to visualize what's going on. But before we start to solve this geometry, problem, we're going to apply law of size. But when we apply law of size, we need to know which triangle we're actually dealing with. So for now, what we're trying to deal with is actually this one. And draw an additional line over here. This is going to be the triangle that we're going to deal with. Let's put it over here. So I got A2 over here, I got A3 over here. Can we know the third length over here, which is slope? We can get that easily because we also know the length over here, it belongs to the big triangle over here. So this one over here must be R squared plus S squared. Let's put it here as well. So when we have those information, which angle in this triangle has something to do with theta 3? We can know the phi over here is something we target because theta 3 in this case can be treated as 180 minus phi. So if we know those kind of relationship within the system, then we can start to solve for the answer. Let's use another color for solving this one. So we're going to apply law of cosines. What do? We are having the slope square. So this square is going to be equals to A2 square plus A3 square minus 2A2 A3 cosine phi. That is something we're going to have. So if you move cosine phi to the other side and do a little bit calculation, what we're going to do is to have R squared plus S squared minus A2 squared minus A3 squared divided by 2A2 A3 minus equals to cosine phi. So when we are using this configuration over here, it would be straightforward for us to figure out what's going on as phi. Let's just take our cosine of this specific calculation. If you do that, you're going to find the answer is actually phi equals to cosine get the correct. 2A1, A3, and the other part of the information becomes this. Okay, so theta 3 is going to be 180 minus v. That would be something that we're going to do. So after this one is solved, we're going to solve for theta 2. But theta 2 cannot be solved intuitively. So we're going to use another method to come up with the answer. This time, we still try to figure out the relationship within this triangle. But this time, there are a few things we need to know. Let's assume this one is alpha, and the overall angle between this side and this one is beta. Clearly, theta 2 plus alpha equals to beta. Theta 2 equals to beta minus alpha. That will be something you are looking for. And once we get this specific information, the other part of information is that since we know this is alpha, we can start to apply law of size. Psi alpha corresponding to A3 R squared plus S squared over here corresponding to V. So with those information defined, we know that psi alpha is going to be A3 over S squared plus R squared psi phi. Since phi has been derived in the previous part, so I can treat this one as a known number, which means alpha is going to be arc sine A3 R squared plus S squared psi phi. That would be this would be the answer for this part. Then we're going to have theta 2 equals to beta minus alpha. That's it. So we can solve for your angle using this method. You can see that all the steps are not systematic approach. We just try to use a triangle to figure out what's going on. So sometimes instead of using this specific configuration, and you try to figure out what is the number of theta 2 and theta 3, we can use another additional method. So go back to a previous slide over here. So when we try to find theta 2 over here, you have no choice but trying to find alpha and figure out what the beta is, because theta 2 is not always intuitive to be derived. So let's draw few lines over here. Let's say this one is a right angle. So we know this is A3, and we know this is theta 3, and theta 3 has been solved over here. So this big triangle over here, this one is going to get A3 sine theta 3. This part over here is A3 cosine theta 3. So with this specific configuration, we got A3 sine theta 3 over here. We got A3 cosine theta 3 with the angle over here is theta 3. Over here, this is alpha. The length over here is 8. Let's erase that. Sorry for that. This is actually A3. This is actually A2. So with this specific information, it's straightforward for us to do. We can start to do tangent alpha. Tangent alpha is going to be height divided by bottom. So in this case, I got A3 sine theta 3 as my numerator. The denominator is going to be A2 plus A3 cosine theta 3. So alpha is going to be arctangent A3 sine theta 3 over A2 plus A3 cosine theta 3. Either way, you should be able to find the answer, and beta is still inverse tangent R over S. So theta 2 is beta minus alpha equals to arctangent R over S, arctangent A3 sine theta 3 A2 plus A3 sine theta 3. So this is the first example we calculate for the parameters using inverse kinematics. As you can see, we do not have any kinematic equation involved. Everything we're dealing with are pure geometry relationship and things like that. So with that said, how can I guarantee everything is going to be correct one? I can tell you it's not, because even though it's only 2-bar linkage and it can actually look like this kind of a robotic arm. So when I solve for the problem, the way I draw that on the diagram like this is because I assume it's going to be moving in this way. However, there is no guarantee. It must be moving in this way. So this one shows 4 possible configurations how your robotic arm is going to be positioned. So with those positions, we can always have something to come up with and have the end effector point to the same location. So for this kind of problem, if this is a design problem, then you shouldn't have any, you should have more than one answer that you need to do. Let's work on a second example. The second example is similar to the first one, but this time it's a little bit different because when we try to do something like this, we have 2 rotational movement, but the third one is a linear displacement. So we are given xc, yc, and zc. We try to find theta 1, theta 2, and d3. So for this specific configuration, some part is identical to a previous problem. The first thing you need to do is to determine what is theta 1. Tangent theta 1 should be pretty straightforward because it's going to be y naught divided yc divided by xc. Then that is the first part of the solution. The second part of the solution, we also need to project everything onto a two-dimensional plane. So the idea is identical to the problem we solved earlier. This is horizontal, not x. This one over here is going to be z naught. So if we draw everything over here, this is something we're looking at. And this is going to be my theta 2. If this is s, this is t. Okay, so with this specific configuration, let me draw the configuration on this side. This one over here is going to be S. Okay, and this is going to be my theta 2. And this is going to be my D3. D3 is pretty straightforward. That is going to be s squared plus square and take a root of the combination. Then the second one is we need to figure out what is theta 2. Now, since we use tangent all the time, you should have a better idea what the tangent is going to look like in geometry representation. So when we are doing tangent theta 2, what we're actually doing is this one is S, this one is R, but this one over here is actually ZC minus D1. Okay. So go back to the previous slides. The length from here to the end effect. The length over here is going to be xc squared plus yc squared plus zc squared. It will be something we might want to understand what's going on. So when we are doing something like this, we actually have the total length that is going to be x1 sc squared plus yc squared plus, you cannot use zc over here because the step might not know what's going on over here and might not know zc, whether zc can be kept as a constant. So over here, in order to find this one in three-dimensional space, we have xc squared plus yc squared plus z1. Actually, it should be a zc squared, but since we are not start everything from the root of the robot, so over here it is going to be zc minus d1 squared. We talked about this one in the previous slide. So this is going to be the length from this point to this point, which should be covered in your high school, in your middle school. What is the denominator? The numerator. This one over here is actually this one. So theta 2 is pretty straightforward. Okay, so this would be the answer. Okay, so let's take a break. Then we're going to understand or realize what's going on for the system with more than one joint, or the configuration is actually much more tedious. We can only use triangular functions to figure out how to get everything start to be calculated. So that's it.